All right, so we're gonna go back a step and we're gonna do 2.6 ratios, rates, and conversions. So by now you should know how to solve proportions. All right, so we're gonna keep working with some fractions and we're gonna solve some problems. We're gonna solve some unit rates, learn conversion factors, and all that. All right, so an important review is going to be to know how to work with fractions, know how to write a fraction in simplest form. All right, so in this review, we want to first write a fraction with a numerator of 12 and a denominator of 13. This should be super easy review, right? So we should know that a numerator is a number on top and a denominator is a number on the bottom. So we get 12 over 13. All right, and now let's circle fractions that are in simplest form. All right, let's go one by one. 15 divided by 30. This is not in simplest form, right? You can still divide the top and the bottom by a common divisor. All right, so 5 over 18. This one is in simplest form, right? So 5 and 18 don't share any other common factors besides 1, right? So this is one of our fractions in simplest form. All right, now 17 over 42. This one is in simplest form, right? Because 17 doesn't have any other factors other than 1 and 17, right? 1 times 17 gets you 17 and nothing else, right? So 17 is not a factor of 42, right? So this cannot simplify anymore. This is another fraction in simplest form, all right? And 22 over 33, this is not a fraction in simplest form, right? Because we can divide the top and the bottom by 11. And we get whole numbers on the top and on the bottom, right? So we get 2 over 3, right? So 22 over 33 is not in simplest form. All right, so number 3, a fraction that is in simplest form only has a common divisor of 1, right? And if you don't know what that means, if we have a fraction in simplest form, let's just say 2 over 5, right? Can they be simplified anymore, right? 2 over 5, do they share any other factors, right? They don't, right? The only factors that they share are 1, right? So essentially we can divide both of these by 1, but that's not going to change anything, right? So we still get 2 over 5, right? So this is a fraction in simplest form. They only share a factor of 1. All right, so that's just some review on fractions. All right, so you'll hear the word rate a lot in this lesson. So a rate is a ratio that compares quantities measured in different units, right? This is the key thing here that kind of separates rates from any other kind of ratios, right? So we compare quantities in different units, right? So something, for example, is miles per hour. You maybe see this when you're in a car and you see the speedometer, the miles per hour, right? So 45 miles per hour, one of our units is miles and our other units is hours. So we have distance and time, right? So that's an example of a rate, right? More examples are miles per gallon. So you maybe hear this with gas, like gas mileage of a car, right? Cost per ounce. If you're trying to find the cheapest option in a store, right, and you see various different sizes all priced at different prices, right, you maybe see also that there's a cost per ounce listed, right, and that's just the amount of dollars that you're spending per ounce of whatever you're buying, right? So that's we call that a unit price, and we'll go there later on in this lesson, right? And then words per minute, right, how many words that you can either read, or maybe you see this with typing, right? When you guys learned how to type, if you did, right? Words per minute is the amount of words that you can type per minute. Again, units are words, and the other unit is time, right? In minutes. All right. And here's some examples using symbols. So this is going to be the most useful to you guys in terms of math, right? But in like just speaking, colloquial language, you maybe hear people say these more. Right, but in this class, you're going to see these listed as some rates, right? And, okay, so let's actually write a rate for each of these situations, right, just to get used to working with these. All right, so Chandler bicycles 20 miles per hour, right? Miles is one of our units. Per hour is another unit, right? So we have 20 miles per 1 hour. All right. Number 5, Anne makes 80 bagels every 3 days, right? One of our units is bagels, right? And she makes 80 of those. So 80 bagels. Every is going to be for every 3 days, right? Days is our other unit, so over 3 days. All right, so those are our rates. All right. And this last one says, so far you've read 35 pages out of a 50-page assignment. Explain why the ratio 35 pages out of 50 pages is not a rate. All right, so I want you guys to think about this for a minute. All right. Now, look at the units here, right? So we have pages here and we also have pages here. Right, so 35 pages out of 50 pages, right? These are the exact same unit, right? And if you look up here, a rate is a ratio comparing quantities in different units, right? So this is not a rate. And you can say just that, right? So it's not a rate because the units are not the same. All right, and that's it for this page. All right, let's keep going. So let's put this into practice, right? These are the most useful in word problems, right? You might only see word problems here in this section, right? Because that's where this is, this has maybe the most real life application directly to you guys, right? But this first problem says the prices for one shirt at 3 different stores are shown. If store B lowers its price to $42 for 4 shirts, which store offers the best deal? All right, so as of right now, the way it's written, the price for one shirt before store B changes its price, right? The price for one shirt, it looks like store C has the lowest price, right, per shirt, right? So I would circle store C, right? $10 for one shirt is lower than the other two, right? But store B lowered its price to $42 for 4 shirts, right? So let's set it up in this proportion, right? And we've seen something like this already in 2.7, right? So if the cost is on top, then we want to put $42 up here, right? And if the number of shirts is down here, then the number of shirts is going to be 4, right? Because it's $42 for 4 shirts. All right. And then to find this missing piece right here, right, you can kind of do it the way that we've been doing with the proportions, right? So you can think of it as 42 divided by 4 equals x over 1, and just solve this, right? So we get 42 times 1 is going to get us 42 equals 4 times x is going to get us 4x. And then you want to divide, right? If you're dividing both sides by 4, right, divide by 4, we kind of end up with the same thing, right? But now you have kind of a clear picture of what's going on, right? So divide 42 by 4, right? It should go in to 42 10 times, all right? And then you want to keep going with this one, right? So you want to actually make it a decimal because we're talking about a price, right? And price is not just measured in dollars, but we can do cents as well, right? So let's add 42.0 and let's bring down a 0, right? And then 4 goes into 20 5 times, right? So it becomes 20, which is 0, right, as our remainder, right? So our total price here for 4 shirts is going to be $10.5, right? So up here we have 10.5 or 10.50. right, dollars per one shirt. All right, now which store offers the best deal now? All right, it looks like it's still going to be store C, right, because we have $10.50 for one shirt, but that's still not as low as store C, right? So store C would still have the lowest price. All right, so let's just write that down in a sentence. All right, so why does the store have the best deal? All right, store C. All right, you can write it however you want to get the point across. All right, but store C still has the lowest price per shirt. All right, something like that. All right, so that was one example problem. Now let's start conversion factors. All right, so this next section right here explains that a conversion factor is a ratio of two equivalent measures in different units, and the conversion factor is always equal to 1. All right, so that means they are equal. All right, so let's complete each conversion factor. We should know these. All right, how many inches are in a foot? All right, hopefully we know it's going to be 12 inches. All right, how many miles are in 5,280 feet? All right, it's going to be 1 mile. All right, and then how many centimeters are in 1 meter? All right, hopefully we know this as well. It's going to be 100 centimeters. All right, and then how many hours in 60 minutes is going to be 1 hour for every 60 minutes? Right, so these are conversion factors. That means these are the same, right? If 1 foot is the same as 12 inches, then this fraction is equal to 1. All right, so now if we want to convert units, right, let's try to solve this problem here. All right, so what is 1,250 centimeters converted to meters? All right, so we first want to know how many centimeters there are in 1 meter. All right, there are 100 centimeters in 1 meter. All right, and all right, these are all step by step how to do it, right? So when you convert from centimeters to meters, the number of meters will be, what do we think? Less than or greater than the number of centimeters, right? Should be less than, right? Because if there's 100 centimeters for 1 meter, then if we have a lot of centimeters, we should have way less meters, right? And we're going to see that now, all right? And then the next one, number 14, when you convert from centimeters to meters, the appropriate conversion factor will allow you to multiply/divide out the common units. Again, what do we think here? All right, we should be able to divide out the common units, right? Again, if you're confused, we're going to do an example now. All right, we're actually going to solve it. All right, so the conversion factor from converting from centimeters to meters, if you are given centimeters and you want meters, that means you're trying to divide out the centimeters, right? So to divide out the centimeters, you want centimeters on the bottom, right? So 1 meter per 100 centimeters would be the correct conversion factor, all right? And B would be wrong because 1,000 centimeters are not in 1 meter, all right? And C would be wrong because we already have centimeters, right? And if we multiply it by this conversion factor, then we're just going to end up multiplying the number of centimeters by centimeters again, and we're going to have more centimeters, all right? But the goal is to cancel it out, all right? Same thing with answer choice D, right? It's a combination of the other two. 1,000 centimeters is not the correct conversion factor, and we're trying to cancel out the centimeters, all right? So the correct answer here would be A. All right, so let's complete this conversion. All right, so we want to convert 1250 centimeters to meters, right? So we want meters, so let's keep meters up top. So 1 meter divided by 100 centimeters. Keep in mind this doesn't change our value, right? And then now we end up just getting, we can multiply straight across, right? 1250 times 1 meter. So 1250 centimeters times 1 meter, all right, over 100 centimeters. Right, think of it like the unit's going to cancel out, right? There's no unit anymore. There's no centimeters. There's only meters, right? So we have 1250 times 1, which is just 1250, divided by 100 meters, right? So let's actually try this, right? If you can't do it quickly, then do your long division, right? So 1250 divided by 100, 100 goes into 1250. So far it's going in once, right? And then 250, right? Bring down the 0, goes into 250 twice. All right, so we get 250, and then have a little decimal point, right? There's nothing wrong with decimals here. Here I do want the decimal. I think I told you guys before, like, I don't care about the fractions, right? But here, these are real world situations. You do want to keep going and you want to get a decimal answer. All right, so we get 12 point, 100 goes into 500 5 times. All right, and then how we finish. All right, so we have 1,250 centimeters is the same as 12.5 meters. Again, you see that we're going from a bigger number to a smaller number, right? So the number of meters was less than the number of centimeters, and to do it, we divided, right? We did 1250 divided by 100, all right? And that's how you're going to solve all these problems. All right, so let's have a look at this one. Now, we want to, in this problem, okay, it says the Sears Tower in Chicago, Illinois is 1,450 feet tall. How many meters tall is the tower, right? So we're going to be converting from feet to meters, right? So it tells us that 1 meter is the same as 3.28 feet, right? So let's use this in a conversion factor, right? The conversion factor we said is a ratio, right? So we have right now 1 meter over 3.28 feet, right? This is our conversion factor, right? And to find the height of the tower, we're going to divide by the number of feet, right? We're given feet and we want to get rid of feet and we want an answer in meters, right? So we get 1 over 3.28 feet, all right? So now let's give this one a try. All right, so now let's divide, right? We end up dividing 1,450 by 3.28. All right, so 3.28 divided by 1,450. All right, and to divide a decimal, we want to move the decimal over, right? We can't really do anything with it as is, right? So imagine there's a decimal place right here, right? So we want to move it over 2 units. Right, if we did that to the divisor, right? So we should get 0 0 right here. All right, and this should have been 28. Sorry about that. So yeah, 3.28. All right, so now let's start dividing. Right, looks like it doesn't go into 1 4 5, right? But it goes into 1,450. All right, we can give this one a couple tries. Right, so let's just test out a number, right? Let's say maybe 328 times, let's try 4. All right, 4 times 328 is going to get you, what, 32 up top, and then 4 times 2 is 8, plus 3 is 11, and then 4 times 3 is 12, and then 12 plus 1 is 13. All right, and it's not going to go any higher, right? We kind of got lucky with this one, or I kind of got lucky with this one. All right, so it goes into 1,450 4 times. All right, so we get 1,312. All right, so we should get in our answer, all right, you can bring that over. It's going to be 4, and then 10 minus 2 is 8. 4 minus 1 is 3, and then 4 minus 3 is 1. All right, and then just bring down the 0. All right. And now it looks like we kind of got lucky again, right? 1,380 is not far off from that 1,450 that we just found, right? So let's use the exact same number, right? It goes into 1,384 times, right? 1,312, right? Subtract that from 1,380, right? So we should get, looks like we get 68, right? And then we bring down the last 0. All right, let's round to the nearest meter. All right, so after this one, let's just round it, right? So 680 looks like 328 could go into 680. I would say 2 times, but we can check, right? So 328 times 2. All right, we get 16, and then 2 times 2 is 4 plus 1 is 5, and then 2 times 3 is 6. Right, 656 looks like it works. Right, so we want to get 356 here. All right, and then simplifying this should get you 24. All right, so let's see where exactly to round it, right? So let's try 0.0 again, right? So point, and we're just going to do this to round to the next whole number, right? And it doesn't go into 240 any times, so 0.0, right, that's fine, right? Let's just keep this as our answer, right, because it's going to round down to 442, right? So it is approximately 442 meters, right? So if the height of the Sears Tower we got was about 442 meters. All right, so let's look at the next one. Right, an athlete ran a sprint of 100 feet in 3.1 seconds. At what speed was the athlete running in miles per hour? So we want to round to the nearest mile per hour. Right, so let's circle what we know, underline what we want to find out. We know what? So we know that the athlete ran at 100 feet in 3.1 seconds. Right, so we have the speed in feet per second, right? So let's circle that. Right, and we want to know at what speed the athlete was running in miles per hour, right? So let's underline this one, speed of the athlete in miles per hour, right? So we know the speed in feet per second, but we want to find the speed in miles per hour. All right, so when writing a conversion factor, if the unit to be converted is in the numerator, then the unit should be in the, what do we think, numerator or denominator of the conversion factor. Right, this one should be in the denominator, right? Keep in mind, guys, we want to divide out the unit that we're trying to convert from, right? So if we're trying to convert from feet per second, right? So if feet is on top, then we want to convert with feet on the bottom, right? So we're going to perform two conversions to solve this problem, right? So we want to convert or circle the conversion factor to convert to miles per second. And we want to underline the conversion to convert to miles per hour, right? So first we're converting from feet to miles, right? So we're going to be using this one right here, right? So let's circle, I didn't really circle it, I boxed it, right? But let's circle this one, right? We're going to use this one. We want feet in the denominator, all right? And once we have that, we have seconds in the denominator, right? So this one we actually want seconds in the numerator to cancel it out from the bottom, right? So we're going to use this one as well, right? So we're going to underline this one, and we're going to use the conversion factors to solve the problem, right? This one's a little bit longer, right? So first we have 100 feet per 3.1 seconds, all right? So let's multiply this by our first conversion factor, right? We want to convert from feet to miles, right? So we get 1 mile per 5,280. All right. And now to convert this, we want to treat it just like a fraction, right? So 100 times 1, right? If you're multiplying fractions, you can go straight across, right? So 100 times 1 is 100, divided by 3.1 times 5,280, right? So we can do that right here, right? Right, times 3.1, right? And then 1 times this whole thing is going to get us the exact same thing. And then 3 times this, right, drop the 0. This is going to get us 24. Right, so something like this. Right, so we should get something like this. And because we had a decimal place, we want to move it over 1. Right, so we get 100 over 136,000, or 163,680, right? And this is in miles per second, right? But we want to convert from miles per hour, right? So now let's multiply by another conversion factor, right? So we're going to do times. All right, so we're going to do times. Our second conversion factor was this one right here. It's going to be 3,600 seconds over 1 hour, right? And if you notice, right, and the same thing happened over here, right? And I forgot to write the unit, right? Feet went down here, right? The feet and the feet are going to cancel, right? If you have feet on top and feet on the bottom, then you're just left with miles on top and seconds on the bottom. Same thing here, right? We have seconds on the top, seconds on the bottom. So we're left with miles on top and hours on the bottom, right? So on top, anything times 100, you just want to add 2 zeros at the end. So this becomes 360 0, and then we want to add 2 zeros. What number is that? 360,000, right? And then divided by 163,680. All right, I know we've been doing a lot. Let's actually, all right, I don't want you guys to divide all this out. At this point, just use a calculator, just approximate your answer. And it's at this point that I noticed I included the 0 when I shouldn't have. Right? It should just be 16,368, right? Because we moved the decimal place over 1. All right, sorry about that. So yeah, just get rid of that last 0. Right, and then just divide this out. Right, so when you divide this out in your calculator, you should get approximately, right? So the squiggly equal sign just means approximately 22 miles per hour. All right, and that's what you get for this page. All right, so let's get into a concept. All right, so let's answer this question. Does multiplying by a conversion factor change the amount of what's being measured? All right, how do you know? All right, if you remember what a conversion factor is, this answer should be obvious. All right, but let's start. Let's circle any equation that's true. Right, 39 times 1 is 39. Anything times 1 is itself, right? So this one's true. Right, 1 times x equals x. Again, right, anything times 1 is itself. All right, this one is true. Right, x times 1 is x plus 1, right? This one would just get you x, and then this one you can't simplify anymore. So x equals x plus 1, this is not true. All right, and then 5 divided by 5 times x equals x, right? And 5 divided by 5, what does that equal? That just equals 1. So you get 1 times x equals x, and 1 times x is just x, right? So x equals x, right? And this is a true statement. All right, so 3 out of these 4 are true. All right, and then one thing you need to know, a conversion factor is always equal to 1, right? We covered this in either the previous slide or the slide before. All right, a conversion factor is always equal to 1. We have the exact same thing on the top and on the bottom, just with different units, right? So multiplying by a conversion factor does not change what is being measured because you are multiplying by 1, right? And multiplying by 1 doesn't change anything. All right, so let's try this last problem. Right, so this one says if you convert pounds to ounces, will the number of ounces be greater or less than the number of pounds? All right, so how many ounces are there in 1 pound? All right, there's going to be 16. Right, if you didn't know that, it's going to be 16. All right, and now we want to convert 2 pounds to ounces. All right, so we want to multiply by a conversion factor. Our conversion factor here, right, 16 ounces is the same as 1 pound, and we're trying to cancel out the pounds. Right, so we have 1 pound on the bottom, right, and we want 16 ounces on the top. Right, and then pound is going to cancel with the pound, and then you get 2 times 16. 16 divided by 1 is just 16, so 2 times 16 is going to get you 32. Right, so you get 32 ounces. All right, and now let's do the reverse. Let's convert 48 ounces to pounds. Right, so if 1 pound is 16 ounces, this time we want a pound on top. Right, and we want ounces on the bottom because we're trying to cancel out the ounces. Right, and then we get 48 times 1, which is 48. 48 divided by 3, you can divide it by 16. I just said it. You can do it off to the side, but this should get you 3 pounds. All right, so let's complete the sentence. Right, underline the correct word is going to be if you convert pounds to ounces, the number of ounces will be greater than the number of pounds, right? As we can see, right? 32 ounces is clearly greater than 2 pounds, right? 48 ounces is clearly greater than 3 pounds. All right, so your answer here, right, it's just going to be a little sample. But you could say something like, if converting from a larger unit to a smaller one, you have more of a smaller unit. All right, so we see that there's 16 ounces in 1 pound. So 16 is our smaller unit, and we have more of those to reach 1 pound, which is our bigger unit, right? So it's going to be something like that. All right, so now This last part is just for your review, but otherwise that's it for this lesson.